We are going to continue. We talked about the limit at infinity the other day. That was section 3.6. We have kind of two more sections from this chapter that we're going to finish it today. Then be prepared for the second part of the course. Okay. I've just seen that some of you already got your test done. So you know that this is going to be the second day, second window, if you like. And you have today and tomorrow to take the test number 2. And we're just working on these sections to be able to finish them on time by the end of this week, so that you'll be able to start talking about your next quiz. Okay, so let me just go to any question. So let's go to my notebook, then I tell you what we are going to do today. There are 3 easy sections that we are going to try to cover, or 2 sections. The first one is going to be section 3.7. You see, we already talked about the maximum value and the minimum value of a function. So the question is how we're going to use it in everyday life. The way we are going to use it, there is going to be a situation that you need to maximize or minimize your action, whatever you have. Okay, you're working, for example, you'll be interested in maximizing your revenue or minimizing your cost. And the problem in which you are looking for a maximum or a minimum, we refer to them as optimization problems. So optimization problems are going to be in this course. So we are going to give you just a brief idea. It is very classic. So it depends which discipline are you going to be in future. If you are going to be computer science measures, then you're going to get this course. It's optimization course. It's a 400 course, and you get it when before you graduate. And again, there are some numerical methods to be able to do this type of problems. So there is a part of mathematics we call it numerical analysis that will do all the softwares, if you like, but you have to know the foundation to be able to do it. And there's going to be one version, calculus 3, that we refer to them as Lagrange multipliers. So these are, the future application. But in this course, we are going to give you preliminaries. We try to talk about it in some popular examples, so that we don't need anything, we don't need anything from physics, chemistry, mathematics, geometry, etc. So, and we just test you on the coming test or the quiz. You may see 2 on the quiz, but you may see 1 on the test. Okay, so this is going to be the way we are going to do it. So this is going to be 3.7. Okay, application problems. So we call it optimization problem. That's the expression. Okay, optimization problems. So these are going to be the problems in which there is a quantity that you want to maximize or minimize. So you want to use calculus to do it. So we start with the history of these type of problems. This one, you already seen this example in your college algebra course. It's a famous Fermat problem. The calculus for the way the Fermat talk about it, they start with this problem. But this problem is a very old one, and it was done, you can find it in the Greek literature. Very easy problem. We have a piece of a wire, and we want to make a fence, if you like. But we like to make a fence in the shape of a rectangle. So we want to know how we are going to do it, or which dimensions would give you the maximum area. So we want to make the best of your wire, okay? So we start with this on to format. So the problem is going to be, that's it. You have a piece of wire, if you like. Okay, a piece of wire with a specific length, in this case, 8 inches or 8 yards, etc. okay, is bent, or we are going to bend it, bent into, okay, bent into the shape of, into the shape of a rectangle, of a rectangle. Okay, so what we'd like to do is which dimension, okay, which dimensions would give us the largest area, which dimensions produce, okay, produce the rectangle, produce the rectangle of maximum area, of maximum area. That's basically one of the version of that famous problem. Okay, so you have to put this problem into the graphical form if you like. So what you have, this is a wire, and that would be 8 inches. Okay, this is the wire that we have. We are going to bend it into the shape of a rectangle. So this is going to be a rectangle. So this rectangle would have a dimension. So you have to label the dimensions as X and Y. Okay, so the area of this rectangle, the area of a rectangle is a product of dimension. So what we'd like to do is, you would like to do it so that this area is going to be a maximum. So we would like to, to cover or to fence the largest part of your area, your house, your home, your land, okay? So this is it. We would like to make this one is, or make it as a maximum. So the largest possible area. Again, that's what. Yeah, fair might start with this one, but the other problem that he got is he just divided this wire in 2 parts. He make a circle and a square. Then he asked for the radius of a circle and the dimension of the sides of the square, so that the sum of the areas are going to be a maximum. That would be a nice problem, okay, to form. But we would like to give you just one from these categories, but you may see it in your book. So this is it. The way we're going to handle this type of problems in calculus 1, of course, is the quantity that you want to maximize or minimize. You are going to make it as a function. Okay, so because you need a function. So you can stay with the A, or you can introduce the usual practice notation of the function. So you are going to suppose your function is going to be f of x equal to the x times y. You see, that's going to be your function. But your function in all these problems that I'm going to talk about it is going to be a function of 2 variables. If you are going to be in calculus 3, we can do it with a function of 2 variables. And that would be the Lagrange multipliers that I talk about it. But in this course, you can't do it with the 2 variables. So the first thing that you have to do is you have to find a relationship between the x and the y, that 2 variables is given to you, so that you'll be able to find the y or x in terms of the x. Then you bring it back here, make a function into the real f of x, and then use derivative to find the maximum. Okay, it's always the case in these 4 problems that we're going to discuss. So as soon as to write it down, you say, oh, note that. I know that. Note that. Now, what is going to be a relationship that you can make between these 3 numbers? You have the x, you have the y. Do you see x, y, and this 8? Remember, this is the 8. You see, how did you use the 8? This is the 8 inches. 8 inches. This is it. So if you go around here, What is this one? So can you find a relationship between X, Y, and 8? Any suggestion? Where did you use the 8? You see the 8 is here. This is the 8. If you go around a rectangle, what is this number? What do you call this one? Any suggestion? If you add all the sides of a rectangle, that would be the perimeter. So this means where is the 8? This is the 8. Add these numbers together, X, Y, X, Y, the perimeter of a rectangle. That would be equal to the 8. So your relation is going to be twice of the X and twice of the Y is equal to the 8. You see, this is a relation that you have to find it yourself in all these problems. Any question? Now, you value to solve for Y. So what you can do is you can divide it by 2. Okay, divide this by 2. So that gives you 4. So you have X plus Y equal to 4. Then you can find Y. So Y would be 4 minus X. That's it. This is your first job. To find the relation, because you can't do it. If you are in calculus 3, you can do the 2 variables. But in calculus 1, your function is a function of 1 variable. So that's why you have to find the Y. So go back and substitute the Y here, then you have a function. So now your f of X is going to be equal to f of X is X times Y. So it's going to be X times 4 minus X squared. Okay, you distribute it, that give you 4X minus, sorry, it's 4 minus X. Okay, distribute that give you 4X minus X squared. This is it. So we have a function. So this function f of X is going to be equal to the as is, or we can change it into the negative X squared plus 4X. And the restriction on X is the dimension. So X must be positive. Okay. Any question? Now you have a function. So what we'd like to do is, you would like to see where this function would have a maximum. This is calculus. In order to get the max or the mean, you know that you have to differentiate it, find the critical values, then test it to see if it's going to be giving you a maximum. Okay, as soon as you form the function, the rest are going to be your calculus. So you differentiate it. So we're going to find the f prime of X, which is going to be equal to differentiated negative 2X plus 4. This is going to be a derivative. Okay, you let it equal to the 0. You solve this equation that gives negative 2X equal to the negative 4. So X would be negative 4 divided by negative 2, which is equal to 2. You see? So the critical value, if you like, of your function is going to be X equal to 2. So this will tell you that at X equal 2, you may get a maximum, but you have to test it. Okay, all these problems need testing. So you have to test it. What is going to be the testing? You have two choices. You can use first derivative test, or you can use the second derivative test. Looking at the function, of course, the second derivative test is much easier. So we use the second derivative test. For the second derivative test, we differentiate it again. So make it into the f double prime. You see f double prime of X is going to be simply negative 2. Remember, f double prime is concavity. F double prime negative 2, this is a negative number. So this means this graph is concave down. When it's a concave down, you know that you are going to get a maximum. So this means the function would have a maximum. F has a max, okay, has a maximum at what? At x equal to 2. That's it. Remember, we are interested in x and the y. So this is x, you put it over here, you get the y. Okay, so y is equal to the 4 minus x, which is going to be 4 minus 2, which is equal to 2. So the final answer is that x is equal to 2 and y is equal to 2. So this means if you want to get the largest area, you have to do the fencing so that you are going to have a, okay, a squared, 2, 2, a square. Okay, it's a very famous problem in Greek literature and in geometry, and the proof is quite interesting. It's a very old-fashioned one. And the problem is among all the rectangles with a fixed, okay, with a fixed perimeter, the perimeter that we got over here, with the fixed perimeter, the one with the largest area is a square. So that's, that's a very famous problem. And if you check, the proof, of course, is the proof of geometry. It's a very old problem. But these are the idea that was used by Fermat for the first time. Of course, you did this problem in your college algebra or pre-calculus class. But in pre-calculus class, you didn't have F prime. So the way you do it in pre-calculus, we say that this is going to be a, okay, this equation represents a parabola. It represents parabola, and since this is a negative sign, we say that your parabola is going to be curving upward. This is your parabola. Sorry, curving down. So this is going to be the parabola. Okay, and the parabola would have a maximum at this point. This point in college algebra, they call it a vertex. Okay, so this is going to be vertex. And you know that the x value of the vertex is x equal to the negative b over 2a. And in this case, if you go to the equation, this is b and this is a. So you are going to get a negative b is 4, a is 1, 2 times 1. So it's going to be negative 4 over 2, which is a negative 2. Sorry, it's going to be a positive 2 because this is a negative as well. So x would be equal to 2. This is the way you did it in your college algebra course or pre-calculus. Okay, but in calculus, we want to use the derivative of the function. Okay, any question? So that's a kind of warm-up. That's history. That would like you to know it. You can only do these type of problems in college algebra because you're just using the, okay, parabolas. But there is going to be a converse to this problem, which are our interest, and that would be officially our first problem. What's the converse? You see in this problem, it's like two numbers was given to you. The sum of the number was 4. You just want to find the number so that the product would be a maximum. Now we do it the other way around. The other way around would be the product would be given to you. Then you want to minimize this sum. This is officially the first problem that we have, and you have a couple of this version in your book. So I'm going to give you one of those steps. Any question? So it's just for you to get the idea. But your first problem is this one. You get 3 of these in your assignment. Okay, it's a kind of abstract. You can connect it to the geometry again to get that correct problem again. But the resultant function is interesting. That's why we are interested in this example. And that's it. Find 2. The other way around. Find 2 positive numbers or integers. Find 2 positive integers. Okay, positive integer whose product or numbers whose product is 144. Okay, 144 and whose sum is a maximum. Okay, it can be any real numbers, okay, to positive numbers or integers, any numbers. Okay, that would be the converse of the other ones that we considered. Okay, so you have to change it to the symbolic form. So you are looking for two numbers. You can call them X and Y. The product is already given to 144. And you want to minimize it. Sorry, this is a minimum, not a maximum. Is a minimum. Okay. So this is how we're going to set up this problem. Solution. You suppose X and Y are two positive numbers. Suppose you have to change it to the symbolic form to be able to make a function. So suppose X and Y are positive numbers, are positive. Okay, positive numbers such that you see the product is given to you such that the product X times Y is equal to the 144 and the sum, and the sum is X plus Y is a minimum. Okay, this is a popular problem, popular case. In your book, you have two different types of this. One of them is exactly the same, X plus Y is the minimum. The other one is they ask for two positive numbers whose product is given to you and whose sum of the first and twice of the second is a minimum. Twice of the second means X plus 2Y. Okay, so this is, if they want to change it a little bit, this is going to be the case, but it's mostly the sum. So X plus Y, X plus 2Y plus 5Y, all of them would be the same thing. Okay, so this is your problem. Again, quantity that you want to maximize or minimize is going to be your function. The quantity that you want to minimize this time is X plus Y. So you introduce your function to be X plus Y, okay? First, your function. And this is the way you do it on the test. You have to give us a function, remember. So suppose that the function is going to be f of X equal to the X plus Y. This is going to be our function. Again, as we did it for the others, you say f of X, but you have X plus Y. So you have to find the Y for us. You have to find the Y. You get the Y from the information of the problem. Information is that X times Y is equal to 144. So I can find the Y. So Y would be 144 divided by X. It's always the case that at the beginning, as soon as you introduce your function, then you have to go back and find the Y, okay? So if they know that f of X is equal to the X, okay? We suppose this one, that's suppose that, sorry. That is going to be suppose. So we suppose that f of X is X plus Y, then note that this is it. And note that. What do you know? We know that the X times Y is equal to the 144. So that would enable us to find the Y. Y would be 144 divided by X. So in all the problems, you introduce your function as a quantity, but you have to find it. So go back and substitute, you have a function. So your f of X is going to be equal to the X plus Y. What is Y? 144 over X. Restriction of X to be positive. So this is going to be your function. Any question? So read it carefully to see, what is given to you or what are you looking for to get a proper function. And the product is given to you and you are working for the sum. So that's your function is x plus y. Now there you are. You have a function. You want to minimize it. At what value of x to get the minimum, you have to differentiate it. My suggestion is to move this x up, then differentiate it, okay? Or you can keep it, use the quotient rule, but that would be easier. So what I'm going to do, I'm going to rewrite this one as f of x equal to the x plus 144 x to the -1. Now differentiate. If you differentiated f prime of x is going to be equal to, f of x would be 1. Okay, you're going to the power rule, -1, you bring it, you multiply it, minus 144 x to the 1 done. -1 minus 1 would be -2. Okay, so this is going to be your f prime. Any question? Let it equal to 0, so for x. Okay, so f prime of x equal to the 0. So this means 1 minus 144 x to the -2 equal to the 0. You want to solve for x, so you better change it into the positive power first. So that gives you 1 minus 144 divided by x squared equal to the 0. You want to solve for x, you have to get rid of the denominator first. You can multiply both sides by x squared, or you can move it to the other side and use cross multiplication, which is more popular. Okay, so I move it to the other side. 1 equal to the 144 divided by x squared, cross multiply is like, this is 1. So x squared times 1 would be x squared equal to the 1 times 144. 144. Okay, take the square root. X would be equal to the positive -12. But remember, x is positive. Okay, but x is positive. X is positive. So this means you're only one solution. X is equal to 12. Okay, so for this function, it's like a critical value. Question? But you have to test it first. Is it the one that gives you the minimum? If the answer is yes, then you go and find the y. Testing, you lose points, remember, if you don't test it on the test. Testing, of course, second derivative test is easier. You can use also first, but second is easy because this is f prime. You simply differentiate it again, okay? So we have the f prime, I just repeat it again. This is the f prime. Now differentiate again, f double prime. F double prime. What's going to be f double prime? The derivative of 1 is 0. The of 1 is 0, -2 times -144. Make it to the 288. 1 done, which is going to be x to the -3. Okay, if you rewrite it, that gives you 288 over x cubed. Remember, x is a positive number, so this is already positive. F double prime positive concavity means it's concave up. Concave up. Concave up, that give you a minimum. Have to test it, remember. Okay, any questions? So this means x equal to 12, give us a minimum. So f has a mean. F has a mean at, okay, a mean at x equal to 12. Now we can go and find the y. Y was 144 over x. So that give you 144 over x, which is 12. So that give you 12 again. So y equal to 12. Okay, x equal to 12 and y equal to 12 give you the final answer. So again, x and the y must be equal to each other. Any question? Again, in history, this problem is coming from geometry. And remember, this product that's given to you is the area, and this is the perimeter. So in the Greek literature, this is how they create this problem. It said that among all the rectangle with a fixed area, the one with the minimum perimeter is a square. Okay, because you get x equal to 12. Okay, y equal to 12. So again, you are going to have the square in this case. You see, these are the famous, as I told you, a famous problem, the old-fashioned one, and there are some other proofs. But we just pick them because that's easy to handle at this level of calculus. Any question? So we may give you this one, okay? Those three cases that we may give you similar one. This is one of them, and we're going to check. We haven't got any everyday life problems, so the next two are going to be from everyday life. Any question? So again, read it carefully to get the function. You propose your function first. The function is going to be the quantity that you want to minimize or maximize. Read it carefully. So you want to minimize x plus y. So this is going to be your function. Always there is a second variable, you have to find it. So the information is the product is 144. So that enables us to find the y. Substitute, the rest is just calculus. Okay, easy function. I just find the critical value and make sure you test it. You get your result. Okay, question? No. For the everyday life, there is one that's very popular. I have a couple of versions of this one in your book. We call it the poster problem. You see what's going to be the poster problem. Look at this page that I have. You see, the poster problem is, suppose you want to print something. If you want to print something, you go to the printer. When you go to the printer, remember the printer will ask you, what is the size of the paper that you're going to be interested in? The papers are different types, A4, like this one is the most popular one. So you may pick a different paper to do the job. But if you pick a larger paper, you see, if you pick the larger one, then you have to pay for it. So it's going to be more expensive. So what you would like to do is you would like to make sure that you pick a paper. Okay, you pick a paper that save you money and at the same time do the job for you. So you are going to save money. Is your paper would have a smaller area, if you like. So you're looking for the smallest paper, if you like, from the area point of view that will do the job for you. So you are looking for the dimension of that paper. Okay, so that's one we refer to it as a poster problem. So the poster problem, you want to print something on this one. You see, this is it. When you print, this is the printed one. So there is going to be a printed area. This is a printed area and the area of the paper. So what you would like to do is you would like to find out which dimension, okay, which dimension of that paper give you the, okay, what is the smallest area, which dimension would give you the smallest area of the paper. So we are going to save money. When they give you this problem, they show you some information. The information is going to be when you print, you see there is going to be a margin to the right, a margin to the left, margin from the top, margin from the bottom. So they have to give you this information to be able, to get to the problem. So I'm going to describe one of them for you. It's quite an interesting problem. We like it because the way you are going to organize this and get that function is quite interesting. Okay, so it's not bad. Get to know it. You may see it on the test. Okay, this is it. Very famous problem. You have 3 in your assignment. Example, poster problem, we call it. Poster or printed material problem. Let's see, poster problem. Let's see. You have to describe those dimensions, the margin to the right, to the left, so read it carefully. You may have different margin to the right, to the left, or you may have the same number. So read it carefully. This is the case for this one, the top. Okay, the top and bottom. The top and bottom margins. The top and bottom margins of a poster. Okay, of a poster are each 6 centimeters. Okay, it's going to be each, there is an E here. Okay, each 6 centimeter. Okay, so the margin to the right and left are the same, and the margin of the top and the bottom. So 6 centimeters from the top, 6 centimeters from the bottom. And the side margins, and the side to the right, to the left. Side margins. Side margins are again each 4 centimeters. Again, they may be different. Not in this case. Okay, so there are. So the margin to the right, to the left are the same, 4 centimeters, the top and the bottom, 6 centimeters. So what's the problem? The problem is if we have something to print. So what is that? If the area, okay, if the area of printed materials, this is the one that you want to print. Okay, printed material or materials. Okay, this is it. Materials on the paper, on the poster or paper poster is fixed. Okay, it's fixed at what? Fixed at 384 square centimeters. Okay, this is how much you want to print. So the question is going to be find the dimension. You want to make money, save money, so you want to find the smallest possible paper. Find the dimensions. Find the dimensions. Okay, dimensions of the poster. Dimensions of a poster with the smallest area. Okay, with the smallest area. That's it. That's a poster problem. You have to get the graph of the poster nicely to look to see what you have, what you want to do. Okay, already. Solution. Draw a paper like this. You see, this is going to be your, for example, this is going to be your poster. Okay, that's it. Then you get the printed area, and this is something like okay. Almost, it should be the same. I have to move this one a little bit up. Okay, so this is going to be the case. And get the information that we have. Okay, the top and the bottom are 6. So this is 6 centimeters. And this is supposed to be the same, in this case. It's a 6 centimeter, this one too. Margin to the right, to the left is 4 centimeters. So this is going to be 4. Okay, this is 4. And this is also 4. Okay, 6, 6, 4, 4. What you have is the area of the printed material. So it's going to be printed 384 square centimeters. So what's the question? The question is this dimension. Okay, what is the dimension of the poster? You want to find the dimension of the posters with the smallest area, of course, because you don't have to, you don't want to have a big one. Okay. Now, the important part is this part that we're going to use those symbols that represent that dimension. You have two choices, okay? Some people, they go with the X for this one and the Y for this one. And then the area is going to be X times Y, and they try to find the minimum of this. But remember, always we talk about it. You have to connect these symbols that you're going to find. The area is X times Y. But remember, you have to use only one variable. So you should have a relationship between X and the Y that enable you to find the Y. So go to see what is given to you. See, the given one is the area of the printed part, 384 square centimeters. So my suggestion is pick the dimension of this green one, the printed one, as X and Y. You see, you take this one to be X, and you take this one, from inside. This is it, and this one to be Y. Why? Because as soon as you pick these two, you see, if you pick the X and the Y from the inside, automatically you are going to have the fact that the product, the area of the printed material, is what? 384 square centimeters. You see, that's the advantage. Because you see, then if you have this X times Y, then you can find the Y quickly. So you find the Y from here, you see, if you find the Y from here, and that gives you 384 over X, and that would be very useful for you. Okay, any suggestion? So always try to pick the variables going to be connected to the, close to the given information. But you may say that, oh, I need the area of the poster because I want to introduce my function. Now let's see what's going to be the area of the poster. What is the area of the poster in terms of the X and the Y? Now look at this here. You see, this is X. Margin to the right and the left are 4 and 4. Can you give me what is this length here in terms of the X? Any suggestion? X plus 8, very good, yes. You see, this is X, 4 and 4. So that gives you X plus 8, very good. That's one dimension. Now what is going to be this one? Remember, this is Y. This is Y, how far you go up and down. You go up and down as the margin to the top and the margin to the bottom. Margin to the top 6, margin to the bottom is, sometimes it's different. So as we did it for this one, this is Y 6, 6. So it's going to be Y plus 12. So the dimension of the poster is going to be X plus 8, Y plus 12. So the area of the poster is going to be X plus 8 times Y plus 12. This is how you set up this problem. Any question? Make sure you get it. Maybe do it. So we go from inside first. This green one is X. Okay, and this is going to be Y. Why? Because quickly we find out X times Y is 384. Then you have to, but your question is going to be dimension of the poster. So for the dimension of the poster, the outside one. So this length is X, and the leftover to the right, to the left are going to be 4 and 4. So X plus 8. So this is going to be this length here. And the width here, you see inside this portion, green portion is Y, plus the up and down. But the up is 6, the down is 6, so they give Y plus 12. So that make it into the area of the poster. Any question? That's the best choice. Some people, they go with the hard way. The hard way they do it is they take this one to be X. If you take this one to be X, then you have to find the green one. The green one would be x minus 8, and that would be y minus 12. Then this equation would be x minus 8 times y minus 12 equal to the 384. Then you have to solve it for y. It can be done, but it's not going to be as easy as this. That's why I suggest pick your x and the y to be close to the information, because that will enable you to find the y quickly, and that will help you quite a lot, okay? Now, the quantity that you want to minimize is the area of the poster, which is this one. So your function, you see this is the quantity that you want to minimize. So your function, as usual, is going to be this quantity. So now we define our function. Okay, we say suppose, as usual. Suppose the function now is this quantity. Is x plus 8 times y plus 12. As usual, you have to find the y. Then you come back and you say, oh, I have it. Say and note that, as usual, and note that. I repeat that version again. We say that as we did it over here, x times y is 384. So that will enable you to, because we cannot do it with two variables. You can do it, when you learn the function of two variables. Okay, now go back and find the y here, substitute the y. So the function would be f of x equal to the x plus 8 times y is 384 divided by x plus 12. Okay, so this is going to be your function with the condition that the x is greater than 0. And then you have to do the calculus, which is going to be finding the derivative of this function, but you better FOIL it first. Okay, FOIL it, simplify it, and then differentiate it. So it's not going to be a good one as is. Okay, so I'm going to use the FOIL method, multiply, go forward. You know that the FOIL, you multiply these two together and then these two. Then you come back and you do the other way around. Okay, sorry, this is going to be 8 and the other one. So FOIL it. So it's going to be f of x. F of x is equal to, if you multiply these two together, you lose the excess, so you get 384. If you go forward, x times 12, that gives you 12x. Now you come back, 8 times 384. So it's going to be plus. 8 times 4 would be 32, we get a 3. 8 times 8, 64, 67. We get the 6. And 8 times 3 would be 24, and 6 would be 30. Divided by x. Okay, so that's 8 times 384 over x, and then you continue 8 times 12. 8 times 3 would be 96. Okay, so pay attention to this. Make sure they get it right. Now combine the like terms, 384 and 96 would be 480. So the function that you're going to work with is this one. That gives you 480. Okay, 480 plus 12x plus 3072 over x, and the condition that the x is a positive number. This is the function that you have to know. You get a similar one before. Okay, so this is going to be a function that you would like to minimize it away. Any question? So make sure you do the algebra, all right? Since you want to differentiate it, as we talked about it before, you better move this x up. Okay, you move it up and then you differentiate it, because you have to differentiate it twice. One that you are going to find the minimum in this case, and then the one that you have to test it. Any question? So let's continue. I'm going to move the x up to be able to differentiate it easily. So this is going to be the function with when you move the x up. So the function would be f of x equal to it was 480, so it's going to be 480 or 80 plus 12x, and that was 3072 x to the negative 1. This is your function. Differentiate, use the power rule. So f prime of x is going to be equal to lift of 480 would be 0, lift of 12x would be 12, and you just bring the negative 1 down, 3072. Okay, but x to the negative 2. So this is going to be your derivative. Okay, let it equal to the 0 to find the critical value, equal to the 0. So since you want to solve it, change it. So it's going to be 12 minus 3072 over x squared equal to the 0. Again, you have to get rid of the x squared. You can multiply by x squared both sides, or you can move it to the other side, use cross multiplication, which is easier. Okay, so move to the other side. That give it 3072 over x squared. Now cross multiply, x squared times 12 would be 12x squared, and that number is 3072. Okay, divide by 12 to get the x squared. So x squared is 3072 over 12, and it's divisible by 12 in this case. Okay, 2 times 12 would be 24. We get the 62, which is 5. Okay, and that's it. You get the 72, which is going to be 6. 256. Okay, x squared equal to 256, and you take the square root. Okay, that's at 256. If you take the square root, it's I think it's the 16, so positive negative 16. But remember, x is positive, x is dimension, but x is positive, so that gives you the fact that x must be equal to the 16 centimeters. So this is going to be your x. Any question? Now, before getting the y, you have to test it. You have to show that, remember, you are looking for the minimum. So how do you know that you get minimum at x equal to 16? But we know it by testing. If you don't test it, you are going to lose point. So testing, using the second derivative test to test it. So bring the first derivative and just find the second. So this is going to be your first derivative, f prime of x, which is a 12 minus 3072 x to the negative 3. So differentiate it again. F double prime of x is going to be equal to, this is 0. So it's going to negate 3 times this number. Negative would be positive, and we multiply 3 times 2.
I think the first derivative is 2.
Oh, it's 2, yes. 2, negative 2, that's correct. Thank you. So that's first derivative. Now second, this would be 0. Now negative 2, negative would be positive. 2 times 2 would be 4. Okay, 2 times 7 would be 14. So this is it. 6,144, but x to the negative 3. If you rewrite it, 6,144 on the top, x cubed on the bottom. Remember, x is positive. So this is always positive. We usually drop the numbers in it, but this is already positive. So a second derivative positive means a concave, remember? It's a concave up. So you have a minimum. Remember, you have to confirm. Sometimes it's not possible. Okay, so we confirm that f has a minimum. Okay, has a mean at x equal to the 16 centimeters. Okay, so we get the confirmation. Now we can go and find the y. Okay, but remember the y was 384 over x. Now you substitute, that's going to be 384 over 16. This is also divisible. 2 times 16 would be 32. 64, that give you 4. Okay, so y would be 24 centimeters too. Okay, so x must be 16, y must be 24. Any question? Some people, they stop here, but there is one more step to go. Remember that this x and the y was for the printed parts. You remember this one? You are interested in the dimension of the poster. So you have to add the margins to the x and the y. So the dimension of the posters are going to be, your x is, you see x plus 8 is 16 plus 8, which is 24 centimeters. And y with the margin was y plus 12. Okay, so that's going to be 24 plus 12, which is going to be 36 centimeters. So eventually the dimension of the poster, okay, dimension of the poster are going to be 24 centimeters and 36 centimeters. Just make sure to add these quantities to it, okay, to get that part. Okay, so it's a quite interesting problem, and they like it because it's mixed together with those function part, everything you have. So that is why it's very, very popular to get this this part done. Okay, so that's a famous poster problem. Any questions? We have one more. Let's do that one too. So we finish this section, then we give a break. We come back and we do the last section of this chapter. Now, this last one, you are not measuring business. Okay, when we teach this course for the business calculus, we usually give them this example, but it's not bad to know it, because again, you don't need anything to know about the business. I mean, just a commonly known one. And it's interesting the way you are going to set up that function for us. And you already saw this one in your pre-calculus class. That's the case that you're selling something. You see, when you go shopping, sometimes they propose some incentive, okay, give you some discount, some rebates. So if you are the manager of the store, you should think about it. How far are you going to go? How far are you going to bring the prices down, or sometimes bring it up, to make sure that you are going to make maximum revenue, if you like. Okay, so this is the one that we call it maximum revenue problem. The revenue, you have to know only that, for example, if you're selling, let's say, cell phone, if the price of each cell phone is going to be $1,000, and if you sell 5 cell phones, so your revenue would be 5 times $1,000, which is $5,000. This is the only thing that you have to know for this problem. Okay, so again, it's not classic like the one we do in business, but it's nice because you have to set up this problem yourself. So we are going to create a case. You're selling something, then you give some rebate, some discount. We want to know which price would maximize your revenue again. So I just pick one of them. You have a couple of them in your book, and you will see them in your next practice one. So this is going to be the last example that we are going to consider. Again, as I told you, we just give you the idea. It depends what you want to do in future. Okay, which disciplines are going to be. And if you get serious, of course, you have those optimization theorem, and then those softwares for more interesting problem, not this group. Okay, so what is the ones we call it? We call this one maximum revenue problem. Okay, maximum revenue problem. So these are the only 3 that we consider. You have quite a lot. That would be enough to give you an idea. Now, what's going to be this one? So you have a business and you're selling something. Let's describe the problem first. So a business, okay, we have a business sells 2,000 units. Okay, units of a kind of product, whatever it is, of a product per month. Okay, per month at a price of at a price of $10 each. Okay, $10 each. That's it. So you're selling, something like markers, etc. So you're selling the business selling 2,000 units per month. The price of each is $10. So the business will make $20,000 at the end of the month. Okay, so that would be monthly revenue. But they want to sell more. If they want to sell more, they have to give some discount, okay, some incentive. So this is it. It can. So they give you this information. It can sell. The business can sell 250 more items, units, or whatever it is, per month. Okay, per month for each, when you provide any discount. For each 25 cents discount, dollars or 25. Okay, reduction in price. Reduction, okay, in price. Okay, so if you give a reduction of the 20, if you lower the price of each item 25 cents, you get 250 more customers. If you repeat it again, you get 250 more again. Okay, so for the first 25 cents, you get 250. For the second one, you get 250, 250, 250. Okay, so the question is going to be what price? What price would give you maximum revenue? What price? Okay, per unit will maximize. Okay, will maximize the monthly revenue. The monthly, okay, monthly revenue. That's it. Okay, so you want to set the price so that you're going to make maximum money, maximum revenue. That's it. Now, for this problem, the only thing that you have to keep in mind is how we're going to calculate the revenue. You see, I just remind you that. You see, original revenue is just, let me just give you revenue is equal to the what? Is equal to the number of the item, if you like, number of units times price of each unit, price of 1 unit, if you like, 1 unit. So it's going to be number of the unit times price for the unit. So the original one is 2,000 and the price is 10, so that give you 20,000. So you are looking for the new revenue, if you like. So your new revenue is going to be new number and the new price. Okay, so you have to find out what is going to be new revenue, if you like. You see, this is going to be your new revenue. It's the one that you want to maximize it. Now, in order to propose the function, you are going to take the x to be number of the item all the time. That we're going to do those reduction, okay? So you take the X to be. This is going to be number of how many times? Number of 25 cents. Okay, $0.25, 25 cents reduction. This is X. Now you get R of X to be your revenue function. If this is going to be the case, you see, your new revenue is going to be R of X is equal to, you have to find I just write it down for you, see. This is going to be new number of units, times it by new price, new unit price. This is just for your information. You can do it right away. Now, what's going to be our function now? New number of units. You see, previously, the number that you sell is 2,000. So previously, it's a 2,000. What would happen now? You're going to get more customers, more. How many more? 250. But how many times? X. So this is going to be new numbers. Any question? So it depends. If if the number of the customer reduces, it would be negative. In this case, increases, so it's going to be, so originally you're selling 2,000 units per month, but now you get more customers. Anytime you reduce the price, you get 250 more customers. But how many times you reducing the price? X number of the times. Any question? New price. What is the original price? $10. What do you do with the price? Reduction. Okay, reduction. If it's a reduction, minus. If it's going to be increase, plus. How much are going to reduce it? 25 cents. 25 cents. But how many times? X number of times. This is your function. For this problem, you've got to be careful to make sure that you put these numbers correctly. You see numbers, money. And you put the positive negative because the customers increases, price reduces, or sometimes maybe change. So make sure you get this one right. Otherwise, it would be easy to propose, okay? And of course, X is positive because this is going to be number of the time. So what you have to do is, this is your function. You have to maximize this function, so you better FOIL it and then use derivative to find the maximum. Okay, any question? So it's a nice problem, easy, and it's going to be a good one because we wanted to see how we are going to set up the problem for us. Okay, FOIL it. So it's going to be equal to the 20 times 10 would be 20,000. Okay, minus 2 times 25, that will be 50, it's going to be 500 X. You go inside, you multiply these two together, that give a plus 2,500 X. Positive negative would be negative, that's going to be 25, 625 is going to be 62.5 X squared. You can check it in your calculator. Okay, combine the like terms, these two. So your R of X, the function, is going to be 20,000. Okay, that give you plus 2,000 X minus 62.5 X squared. This is your function with the X positive. Question? Differentiate it. Remember, you would like to maximize it. So R double prime, derivative of 20,000 would be 0. Derivative of 2,000 X would be 2,000. And over here, 2 times 62.5, 125. 125 X. This is, sorry, that's R prime derivative. Okay, question? Make it equal to the 0 to find the critical value. R prime of x equal to the 0. So we have to solve this equation, 2000 minus 125x equal to the 0. Okay, move the 2000 to the other side, 125x negative 2000. So x would be, okay, it's going to be 2000 over 125, which is equal to the 16. Okay, so x is equal to the 16. It's the number of the time that you do the reduction. So the critical value of this problem is 16, but you have to test it first. Remember, how do you know that the 16 would give you the maximum? Okay, testing first. Testing. Of course, second derivative test. Second derivative. What's the first derivative? You see, this is the first derivative. I just repeated. Now get the second derivative. If of 2000 would be 0, derivative would be, that's the x here. So that give you negative 125. It's negative. And you know that concavity, negative means none. So you're going to get a maximum. Okay, so you're sure that the Rx has a max, has a maximum at x equal to the 16. Any question? But remember, we are interested in the price. What is the maximum price? What price give you the maximum, okay, revenue? So I write it down here, so I finish it, okay. New price is, remember, $10 minus $10 minus 0.25 times x is going to be $10 minus 0.25 times 16. So it will be like 10 minus 4, which is 6. So the new price must be $6 to make sure that you are going to make money. They usually ask for the price, not the maximum revenue. Okay, so it's again is a nice problem because the way you set it up and make sure your result makes sense. Original price was $10, you reduce it into the $6. So if you have a number which is more than 10, you realize that you made a mistake, okay? So this is kind of give you an idea really of the optimization problems, okay? You just pick one of these, we give you one of them probably on this. Yeah, we give one. So that you make sure you get the idea. So 3 types. The abstract one, we are mostly interested in everyday life problems. So we like to give you something that you see in everyday life. So something like the postage, something like that revenue problem are going to be the case. Okay, any question? So that's optimization problems. We can have a break. It's a 9:18. So come back around 9:30. Then we get the last section of this chapter. Quite interesting for future and not in this course. One part is going to be used in this course, differentials. And the other part that in your book, they talk about it a little bit less, but we are going to talk about it in full. He's going to be using calculus 3 quite a lot. So we discussed that one too. So we give you kind of 2 problems. It's easy section, 2 problems from that on this coming quiz. Then we finish the first part of the course, concept of differentiation. Okay, so see you then to finish that section today. Okay, we're going to continue taking that new section that I talk about it. Any question? So we're done with the optimization problem. This two last section or one last section that we're going to have is the last time that we're going to look at the definition of the derivative of the function again. There are going to be two interpretations that we're going to use in future. Okay, there is a section 3.8, we don't cover it, or that you can read it yourself. It's a Newton method for finding, solution of the equation. It's just a numerical method. You read it for yourself. You're not going to lose anything if you don't know it, but you can check it yourself. Okay, so that's why we go to the 3.9. That's the last section of the chapter 3 and the first part of the course, okay? But it's a true concept that we're going to use in future. So for the last time, we are going to look at the notion of the derivative again. So this is 3.9. In your book, they talk about differentials, but I would like to make it into two parts. So the first one is an operation that we call it a tangent line approximation for future. Okay, that's it, tangent line approximation. It's a kind of numerical method, you see it. Tangent line approximation, or we refer to it, another expression is linearization or linear approximation. Linear approximation. If you intend to take calculus 3, you must know this one. Linear approximation. Let's see, what does it mean? You say you know that so far, and for the last time we were getting to the integration, we remind you that the most important part that you did over here was tangent line. Remember, that was the problem of a tangent line that we started with. That then we talk about the we bring the derivative of the function to be able to find the slope of a tangent line and then write the equation of a tangent line. Let's see what is this concept of the tangent line approximation means. Okay, you see, suppose you have a curve. Let's take this one first. See, that's going to be the pan. You see, in calculus 1, you look at the function of one variable. In a space, in application, you are going to have function of 2 variables or 3 variables. Are going to be in 3-dimensional, for example. Then in that type of problems, the notion of the derivative is difficult to handle. So we use these ideas over there. Now, look at this one. Suppose this graph is given to you, y equal to the f of x. And remember, a point would be given and you find the slope of a tangent line or the equation of a tangent. And suppose this is the given point. Okay, this is the point A. So we'd like to find the equation of a tangent line, and you know how to do it. So this is going to be the tangent line. Okay, this is tangent line. So what I'm going to do, I'm going to call this one L of x. Okay, so I call this one L of x, which is simply the tangent line. Okay, so I can find the equation of this, you know that. This is the point that I have. Okay, this is the point. So this would be f of a. And the equation of a tangent line. So I have a point. Okay, and I can, you see, I have the point here. So my point is going to be a and f of a. Okay, the slope of this line is f prime at a, and I can find the equation of the line. Remember, the equation of the line is going to be y minus y1, which is f of a, equal to the m, which is f prime of a, times x minus a. And I move the f of a to the other side, that give me f of a plus f prime of a times x minus a. You see, that's the equation of the tangent line. So in this case, I'm going to use this new notation, and I'm going to call this one L of x. So L of x is going to be f of a plus f prime of a times x minus a. You see, this is going to be the case. So why I change it? This L would stand for the linear. So what I'm going to do this is going to be called tangent line approximation or linear approximation. We say this is linear. It's the same thing, linear approximation or tangent line. In your book, they call it a linear approximation of the function, okay, of the function f, okay, of the function f at x equal to the a. Now, why we call it linear approximation? You see, this will tell you that if you pick a point, see, suppose you pick a point x here. If you pick the point x here, okay, this is going to be your x. And if you want to find the f of x, so what you can do is you can drop it into the function, okay? So this is going to be, okay, so this red part is going to be, this is f of x, okay, this is f of x. But you can also drop it into the tangent line, because if you continue, that would intersect the tangent line as well. So if you drop the x into the tangent line, that give you, you see, this is going to be, the green one is L of x, the red one is f of x. So what this is going to be giving to you that if you move the x closer to the a, you see, if you bring the x here, if you bring the x here, look at this one. If you bring the x here, you see the difference between that red part and that green part are going to getting closer and closer to each other. You see, if you bring it here, you see, they are going to be exactly or almost the same thing. So the idea is that if you write the equation of a tangent line and you find this linearization L of x would be almost like the value of the function, but with the condition that if x is going to be close to a. So this is a kind of new calculator, if you like. So this idea will tell you that the value of the function around the point A can be estimated by the same value from the tangent line. So this means as you x getting closer and closer to the A, your graph becomes the tangent line, if you like. So that's why we call it linear, we call it tangent line approximation. We call it the linear because you have a curve, then you can estimate it by a linear line, if you like. And that would be so useful in application in science. Okay, so this idea will tell you that linear approximation or the tangent line approximation. This means the value of, if you want to find the value of the function, you can either use your calculator to find it, or you can drop it into the tangent line. Of course, tangent line, you know that what's the equation of a line? The equation of a line is mx plus b. So it would be easier for you to drop it into mx plus b rather than dropping it into the function. So that's the idea of the linear approximation. Okay, so the linear approximation means the value of the function can be estimated. So I write it down, make it official for you, that the definition of a linear approximation is this one. So if a function, it's a tangent line with a new look. If a function, okay, if a function f is differentiable, if it's going to be differentiable, okay, at x equal to the a, then the linear approximation, that's the expression, linear approximation or tangent line approximation of f at x equal to the a is going to be denoted by L of x, linear of x, and is defined, okay, is going to be defined by just the equation of a tangent line. L of x is equal to the, make sure you write it down correctly and bring it correctly to the test. F of a plus f prime of a times x minus a. This is the formula for linearization at x equal to a, or just a tangent line equation. Now, why it is important? This is why it's important. Note that the value of your function is approximately the same as the value at L of x, of course, if you are going to be around a. Okay, so for x close to the a, these two numbers are going to be the same as each other. And it's used, for this type of approximation in this course and in science. Any question? If you are in calculus 3, this would be a very big deal, because in that case, you are going to have a function. It's going to be f of x, y, z, function of 3 variables, and it would help us quite a lot. You see over here, if the function is differentiable, then this condition satisfies. In calculus 3, we do it the other way around. We use this one as a definition of differentiability of a function of 2 or 3 variables. That's why those are going to be important. But in this course, we just give one example to estimate for us, get to know it, but you are going to use it in future. Okay, any question? So to give an example to see how we're going to use it. Very familiar. I go to the next page to get the example. Again, it's going to be useful for future. In your book, they focus on another version of this that we call a differential. But I would like you to give one example. I'm going to question you on this one on the next quiz, because in case you want to take calculus, okay, calculus 3 to see what's going on. Okay, so I'll give you an example. We give you one problem and we ask you to estimate it. And it's always a square root. You see, this is it. Example. That's the example that we are interested in. We ask you find the linear. Find the linear. Okay, linear approximation. Linear approximation of f of x equal to the radical x is like finding the tangent line, same thing. At x equal to 4. It's like finding the equation of tangent line at x. Now then, and use it. Use that one. Use it to estimate. Estimate what? The value of a square root of 4.04. You see, 4 is a point of estimation. Any number close to it, it can be used to estimate that one. Okay, so how are we going to do it? Find the tangent line approximation for that one, or just the equation of tangent line. Solution. You see your a is equal to 4. So get the formula L of x, or the tangent line is f of 4 plus f prime of 4 times x minus 4. This is your formula. Remember, it's a plus. I don't know why some people on the test, they write f of 4 minus f prime. No, it's plus. Like the equation of tangent line. Okay, go and find it. F of x is radical x. Find f of 4. F of 4 is radical 4, which is 2. That's f of 4, like finding the point P2 and 4. F prime differentiated. You know that derivative of radical x is 1 over 2 radical x. Find f prime of 4. F prime of 4 is equal to what? Is equal to the 1 over 2 radical 4. Is going to be 1 over 2 times 2, which is a quarter. It's like this slope. Okay, put it here to get L of x. So L of x is equal to f of 4, 2. F prime, a quarter. X minus 4. Simplify it to get the equation. So multiply this inside, it's going to be 2 plus a quarter of x minus 4 over 4, which is 1. So it's going to be 2 plus 1/2 of x minus 1. So L of x, or the tangent line equation, is 1/2 of x plus 1. This is your linearization, or the tangent line. Question? This is your calculator. Where or when are you going to use it? This is it. You are going to use it that you see, note that you can estimate the value of the function f of x is would be the same as the value of L of x, but only if the number is close to 4. So you cannot use 9, you cannot use 5, 7, close to 4. But what do you want? Any question?
Yeah, is it supposed to be 1/4 x plus 1?
Yes, you are right. Thank you. A quarter. Thank you. A quarter and a quarter. Thank you. L of x is a quarter x plus 1, and you are right. Very good. Okay, so we can use any number close to 4. But what you want, you see, is the radical 4.04. So if you put x equal to the, okay, so you put x equal to the 4.04. So this means f of 4.04 is going to be almost like L of 4.04. But f of 4.04 is radical 4.04 that you are interested in. So it's going to be approximately substitute. So it's going to be a quarter times 4.04 plus 1. So if you simplify this one, that give what? That give 1.0. Okay, so that give you 1.01 in that case. Okay, it's going to be 1.01 plus 1, which is going to be 2.01. So with this calculator that we invented, 4.04 is going to be approximately 2.01. You have to confirm it with your calculator on the test, okay? So calculator result. You use your calculator and find what is the square root of. Okay, what is going to be the square root of 4.04? Okay, so this is it. So we check the square root of 4.04. That's it, 2.009, which is almost like 2.01 that we got. Okay, but write this one from your calculator on the test, just to show us that you did check it. Okay, so it's 2.009 would be fine with your calculator. Okay, and you know that this is going to be almost like 2.01 if you round it. Okay, so that's the idea of the linearizations. So it's very nice to apply, and of course give you a very nice tool to be able to do it. Any question? As I told you, in this course, not much to do with this, but if you go to the 2-dimensional, 3-dimensional in future, because the application that you have in future, especially if imagining physics or any engineering discipline, so this would be very helpful, and this is the way we're going to use it. In that courses, this is of course one variable, use 2 variables or 3 variables to do it. Okay, any question? Now, the way we created here, we give you the function, but you have to find the function yourself. So we just give you this one, and we ask you to estimate it. Easy to find the function because you want to get the idea. For the function, you replace this 4.04 by x, that give a radical x, and you have to pick a number yourself. Number must be close to the 4.04 and nice. Nice means a perfect square. So the 4 is a good one. So I give another one, the way we are going to ask you these type of problems, and you've been asked in this form in your book. Okay, any questions? So it's just a tangent line, but give you a better idea of the notion of the derivative. You see, it's a very interesting interpretation for future. So I give another one. This is the way we expect you to be able to do it for us. And we give you a square root in this course. You see, we just check it because the idea is important, as we told you in future as a theorem. So this is the way you're going to see it in your book and on the coming quiz. And we give you a repeater on the test. Even sometimes I repeat it on the final, but this is a summer course. I don't because I teach calculus 3. I know that I need this one. That's why I repeat it, but we just check it. So this is the way we are going to ask you. See, use linearization or linear approximation. Linear approximation to estimate. Okay, to estimate this one, a square root of 99.4. You have kind of 5 in your book, in your SM. You better pick up at least one of them as those choices that you have, just to check it. Make sure you are, familiar with this concept. It's an easy problem, don't miss it. Okay, linearization. You need a function and a point to estimate. The function, you replace this number by x. So function is radical x, a number. Number must be close to 99.4, and you can have rounded one. Something that would be perfect square, if you like. So close to the 99.4 and the perfect square. What's the number?
100.
Excellent, 100. So this is your job. Solution, you are going to suppose function and a number. Suppose f of x to be radical x, just replace this one by x. And number 100 is close. Somebody will say, oh, I have another one which is closer, 99.3. No, if you check something decimals, you see, you have to use your calculator. We want to avoid that. So we want to pick something nice, perfect square, if you like. Okay, there you are. So write the, like the linearization at 100, then you can estimate it by 99.4. Okay, so just do the job. L of x, the formula for this case is going to be f of 100 plus f prime of 100 times x minus 100. That's the optimization, linearization at 100. So we need f of 100, your function, this is it, f of 100 is radical 100 because of your function. So that gives you 10. You need f prime. F prime of x, as usual, is 1 over 2 radical x. Okay, again, you wanted 100. So that you 1 over 2 square root of 100, which is going to be, that 1 over 20, because that would be 10, 120. So write your linearization, the tangent line. So L of x is going to be equal to the f of 100, which is 10. Okay, f prime is 120. Okay, times x minus 100. Just distribute it, simplify it, that's going to be 10. 1 over 20x minus 100 over 20, which is going to be 5. So it's going to be 10 plus 120x minus 5. So your linearization of your tangent line is going to be 1 over 20x Okay, plus 5. That's it. This is your linearization. Okay, you did it around the 100. So that's it. You claim that f of x can be estimated by L of x, but only if you are going to be around 100. You can't do it for any other numbers. You know, you can do it, but your estimate is going to be way out. Okay, but the number that we are interested in 99.4. So we are interested in x equal to the 99.4 substitute. So f of 99.4 is going to be like L of 99.4 substitute. In the case of the function would be the square root function that you are interested in. And in this case, you just go and substitute. Okay, it's going to be 1 over 20 times 99.4 plus 5. Now it's divisible by 2. So if you divide it by 2, that gives you 10. And divide this one by 2, that gives you 4, 9.2. And there is a 10, so it's going to be 4.92 plus 5, which is 9.92. So with this calculator, a square root of 99.4 is going to be almost, okay, 992.
Isn't it 49.7? Is
Which
that
one?
99.4 divided by 2 is 49.7?
Oh, 7. Yeah, that was 4. 9 times 2, 18. Yes, you are right. Yes, 7. 7. Okay, 7. We are going to check it. 7. 7. Okay, so I relate it. And so this must be 90.97. Just correct my case as well. Okay, but we have to confirm it. We are not done. Okay, confirmation with the calculator. Calculator confirmations. 99.4. And this is calculator. Okay, and so we go with the 99.4. That's it. 9.969, which is almost the same. Okay, so this is our number. So this is going to be 90.969, which is a 99, which is almost the same as 97. Okay, it's good to check it to just make sure you get it right. Okay, you may be a little bit up, but just a little bit. Of course, you know, the number must be around 100. If you pick something else, these are not going to be close to each other, as we showed you by those graphs. Okay, so that's going to be a linearization. Any question? So in your book, as I told you, you know, they talk about it quickly. They don't take this one seriously at this part, but as I told you, it's going to be very serious when we get to the notion of the function of 2 or 3 variables in calculus 3. But the one that is going to be used starting tomorrow, if you like, is the second one, the title of this section from your book, which is differentials. So let's see what's going to differential is something very close to this one. But remember when we talk derivative of the function, we have 2 interpretations. Remember, one interpretation is a tangent line. This is it. The other interpretation is a kind of a rate of change interpretation. Remember that, you know, we give you derivative of the function formula of f of x plus h minus f of x over h. So I'm going to look to that one to see what can you do about the other interpretation for the future or the application in science. This concept is quite important, okay? And this is the one that we're going to use in science, and especially in calculus 3. When we talk about derivative of the function, we are going to be in trouble. But we change the derivative into differential for science, for physics, mechanics, etc. And that makes things so easy for us. Okay, so that's why we would like to have a look at that one too. And of course, going to be used in the second part of the course. So let's see if we can do that one as well. So that was, an extra that we need to know, but we give one question. We are very serious about it because we need it. Now, what is differentials? So it's the same section, but the notion of the differential, this is, you see, as the case with the tangent line, the case with the tangent approximation is very special. But if you want to find something which is more general, is the notion of the differentials. Okay, so I go back, I look at the definition of derivative again, but from science point of view, from the rate of change point of view. And then at the end, I make a differential for you. Let's go back, review what's going to be the derivative of the function as we did it as a rate of change. Do you remember? This is it. Recall that again. Recall that if a function is differentiable, of course, if f is going to be differentiable. Okay, differentiable. Let's say on the domain D, which is differentiable everywhere, then you know that derivative function, the rate of change format, remember f prime of x is equal to what? It was equal to the limit of, that was the definition that we use, f of x plus h minus f of x divided by h goes to 0. That was definition of a derivative in the form of the rate of change. So in this case, we change the x into the x plus h. So we introduced this notation before, but we are going to repeat it again. Remember the change. Okay, the change in x, in the values of the x, in the values, okay, of the values of x is going to be denoted by, we did this one before, denoted by delta x. Okay, delta x, change in x, and the corresponding change in y is delta y. And okay, when we change the x, you get a change on the, okay, on the y too. So, and okay, that's it, the corresponding changes, the change in the values of y is going to be denoted by, delta y. Okay, so that was the one that we did before. So if your function is, if y is equal to the f of x, okay, then the change in y is going to be f of x plus delta x minus f of x. You see, you have the x, for example, x is 2. You change it to the 2.02. So f of 2.02 minus f of 2 would be a change in y. So this delta x is a little bit changed. If you change it, so the difference between the value of y's are going to be the change in y. Now, if you go back and write that the formula again, I don't want to give you the formula right away. I just wanted to see it. So note that the relationship with the derivative f prime of x now is going to be equal to limit of, we change the h into the delta x, so it's going to be f of x plus delta x minus f of x over delta x. Delta x goes to 0. That would be the difference. So this, the top is delta y. So it's going to be the top delta y, the bottom delta x. Delta x goes to 0. It's like the slope of a secant line that we did it before. I just want to give you a notion of a differential. So this simply means you can estimate f prime of x by the the slope of a tangent line, which is delta y over delta x. Okay, and when of course delta x is small, is going to be small. Now, if you cross multiply this one, so this means delta y in this case is going to be almost like f prime of x times delta x. So this is change in y, this is change in x. You see this quantity here, this quantity over here is going to be called differential of the function, differential of the f or differential of the y. And it's going to be denoted by dy. Okay, so this is just, I want just to give you interpretation, not writing down the formula right away. So the quantity f prime of x times delta x is going to be, is called the differential. Okay, it's called the differential. Okay, differential of y or differential of f, not derivative, differential of f, and is denoted notation. Okay, is denoted by dy, differential of y, or df. So differential of y is going to be equal to the derivative of function times delta x. Okay, that would be differential of y. But differential of the x, we can define differential of x is the same as the delta x here. So we define the differential of x, the differential of x is going to be denoted by, dx, differential of the x, and is defined by, and is going to be defined, okay, defined by differential of the x and delta x are going to be the same. Of course, when there is going to be a change, delta x is not equal to the 0. So d of x is differential of the x, d of y is the differential of y. Just put it over here, back here. You get this relationship that you've been using in your book. I didn't, I remember some of you used the notation of dy dx, and I repeated that, don't do it unless you know what it's talking about. This is where we are going to see it. So I put it over here. So what I have is this one. So there you are. dy is equal to the f prime of x times dx, you see? This is a relationship between derivative of the function and the differentials. This equation is referred to as a differential equation. star is called a differential equation. Differential equation. A part of mathematics that dealing with the differential equations is called applied mathematics. So what we're going to do in future is, you see in the first part of the course, the function was given to you, find the f prime. In the second part of the course, starting tomorrow, the derivative of the function would be given to you. We ask for the y. In order to find it, you have to solve this differential equation. You do a little bit in calculus 1, a little bit in calculus 2. Of course, there is a course, I think in your college is 265. And that course is called differential equation in order to solve all of them. But we talk about it later. So, so this is going to be the y, but note that, remember that was a change in y. So we find the estimate for the change in y. Note that change in y is going to be almost like differential of the y. So what we did, we find the estimate for, for this one. It's nothing new really. This delta y is like the linear approximation that we talk about it, okay? It's the same thing, but this would be easier to handle. That gives us a new operator, a new machine to be able to carry the formulas of the derivative when we get things getting complicated. This format is very popular in science. We call it differential form. So we can find the differential of the function, for example, when a function is 2 variables or 3 variables. So they are going to be used in different parts of, especially in physics, in the form of the differential form. And this is one way the calculus was introduced, just using the differential form rather than the derivative of the function. So in order to find that, you just differentiate the function, you write it down in differential form, this form only. Okay, so for example, give you one example. Any question? So it's a kind of a new machine that's going to be used in future. And when you use it, you will see it. In approximation, it can be used as like I'll give you one example to see it, but mainly for the rest of the course, this differential form that we're going to be introducing. You see, when you write it down in this form, we can do the algebra, you can square it, you can multiply both sides by 5, you can divide. You see, if you divide this one by dx, dy dx would be f prime x. So you may say, I haven't done anything because I know that dy dx is derivative. Yes, you can use it as a notation. And that was why I was telling you that don't use it unless you understand it. No, you understand it, that they are the same and you can use it, okay? But the concept are going to be different. Okay, so your job just for the time being is just we are not going to question you anything regarding this one, but use the application. So you have many problems in your books that they ask you find the differential. Find the differential. Okay, differential of each function. Such, of course, important concept for the function of 2 variables or 3 variables in future. But for the 1 variable, you have other tools to get through it. You see, if you see these type of problems in your book and you have quite a lot, this is how they're going to handle it. So y is given to you is x cubed plus 2x squared plus 5. You want to find the differential. You write it down, we say in differential form. So the solution is going to be, so remind yourself that the differential is just a derivative times a dx. So differential of the y is you differentiate whatever rule we have. Power rule is a 3x squared plus 4x derivative of 50 dx. This is differential of the function. Okay, we call it differential form. And as I told you, the reverse is going to be the converse. This would be given to, they ask you for the y. find a function that satisfies this condition. This is the one that we're going to do it in the next chapter, starting tomorrow. Okay, but for the time being, this is all we do. Any question? You may have to use the chain rule. So y equal to 1 plus 2x to the half. You want to find the differential of this function. So the solution is going to be differential of the y is equal to, formula is f prime times dx. You have to use the u substitution, of course, the chain rule, you know that. Just remind you that u to the half is 1/2 u to the negative 1/2. So the differential of the y is, bring the power down, 1/2, 1 plus 2x to the negative 1/2 times u prime is 2, but times the dx. So it's simplify the 2 and the 2, so the differential of the y is going to be equal to the 1 plus 2x to the negative half times the dx. So that would be the differential of the function rather than the derivative of the function. Okay. Again, as I told you, it's going to be quite a lot, this type of equation called differential equations. In applied mathematics, you are going to have two types of equation. These are going to be called ordinary differential equation. We call it ODE. If you see this expression, ODE, ordinary differential equation. If you are going to be in calculus 3, the function of 2 variables, 3 variables, you are going to find the partial derivative. You are going to have something we call it PDE, partial differential equation, ordinary differential equation. You can get a PhD to be an expert in this one or the other one. So such an important concept. Okay, I should give you one more example. To see that the previous problem that you did, we can do with this type of ideas on. Again, we can talk about that problem later. So that would be the end of the first part of the course. Derivative of the function. Okay, so the function was given to you. You just differentiate it. So what we are going to do, we are going to do it the other way around, starting tomorrow. So the other way around would be the derivative of the function would be given. They ask you to find the function. This type of idea, the first one was differentiation. But if you do it the other way around, we call it anti-differentiation. So for the anti-differentiation, we have another expression. The expression is going to be integrations. So that would be our job for the rest of the course. But would like to give you a little bit of that tomorrow, and then we are ready for the for your next quiz. That's it for today. Any question? So read that optimization problem carefully. The problem of a tangent line approximation is easy, nothing to worry about. But we give you a little bit of the integrations tomorrow. One section from the next chapter will be given to you 4.0. Okay, if you haven't done your tests, just go ahead and take it. And I've already received some of them. Then I can look into it over the weekend and give you the result as usual by next Monday. Okay, that's it. Any question? Just let me know if you need anything. Otherwise, good luck and see you tomorrow. Bye-bye.